there anyone in the Zoom?
Yeah, Cole and someone else.
I think, yeah, Max.
Okay, so today Vince and I will be presenting our project, which we presented a couple days ago, but we have some extra stuff here because we have extra time today. So the topic for today will be parameter estimation, specifically for stochastic differential equations, or SDEs. All the SDEs that we'll be working with today have this form. Basically, dxt is equal to some drift term, dxt times dt, plus some diffusion term, sigma xt times dwt, where dwt is Brownian motion noise, or wt is Brownian motion. So in our class, we always focused on problems where B and sigma are known a priori, but today we want to focus on estimating what B and sigma are given some set of discrete observations. So it has some important links with causal inference. Specifically for causal inference, we care more about the multi-dimensional case. So here I took the same equation and bolded xt to show it's a random vector now. So we really care about finding basically the non-zero terms such that we can create some sort of causal graph where this equation 2 basically represents the data generating process. And most of the time we care about estimating B. So in hydrology, B would be this transfer function between rainfall and runoff. But in other cases, like in finance, for solving the Black-Scholes equation, we want to estimate sigma. So both can be important.
What's sigma?
Sigma is kind of the diffusion term, it's called in SDs, and it's basically what the noise looks like. So sigma is being multiplied by this noise term dwt.
So your Brownian motion can change by sigma, right? So the full term can give us diverse noise, right?
Yeah. So it can be like correlated noise between variables or independent, or
And you don't consider linear ordinary differential equation, right? It's not linear, right?
So I'll get to that now, actually. So the goals of this presentation is basically to start easy and then start generalizing. So in the first case, we're going to go through a textbook by Pavliotis and go through 1D processes. They will be mostly linear, but we'll deal with one cubic problem as well. And then we want to generalize to higher dimensional processes with additive and or multiplicative noise.
Yeah.
And that's going to be by going through Wang's paper, which we presented a couple weeks ago. And then we want to further generalize to kind of what we want to do in future work, discussing kind of other functional forms of the SDE.
All right, so as Joe said, we'll start easy. This is how we can do parameter estimation if we only have one dimension, and it's also a linear model. So by linear, it means that the drift is given linearly, and it's given by also a negative coefficient so that it doesn't blow up exponentially. It's also known as the one-dimensional Ornstein-Uhlenbach process. So it's linear in the drift B, and it's a constant in the diffusion. So that just means that we're scaling the Brownian motion so that the variance or volatility just scales according to sigma. So the way that we could estimate our parameters, first we can do them separately. And it's really easy actually to estimate the diffusion in this case because it's constant. It comes from a key insight that in stochastic calculus, if you look at the quadratic variation of a process, you look at basically an infinitesimal of the process, dxt dot dxt. The only thing that matters really is the Brownian motion part, dwt dot dwt, which ends up being roughly dt. And then the other cross terms like dt.dt, dt.dwt, and the symmetric one, they're all vanishing in limit. So what this means is that if you were to write out the quadratic variation, which is you just sum up all these infinitesimal quadratic differences of your process like this, then okay, you can replace it just by in terms of sigma or sigma squared. And then you would get a closed form expression of sigma squared in terms of the quadratic variation of the process. So this is actually exact because it's in limit. Is there a question?
Yeah,
Yeah.
I don't know why DWT.
Oh, it's the Brownian motion scaling. It's
Oh,
that like, yeah.
the square of this Gaussian. Oh, because that's the variance of that Gaussian.
Yeah, I always mix it up. Like okay, so this is that so either space is time squared or time is space squared. I think okay, space is time. The space square root of space is time. It's just the scaling of Brownian motion. And you can do it in limit too. I think if you look at the process like square root WT, you take the you divide it by square root T and you take the limit or lim sup or something, you get a constant. So it's like, yeah. And then yeah,
You
you
don't
can see
need
it.
expectation.
You don't need expectation. This is kind of like, they're just rules of stochastic calculus. I think we just, at this point, can take for granted. There is some, rigorous derivations. I just have some informal understandings.
So how do you, like, when you prove this, like, equation, you expand dx.
Yeah,
Squared?
dxt is here, right?
Yeah.
So if you were to dot it with itself,
So
then
squared means, because it's
yeah,
one dimensional.
exactly, it's one dimensional. I mean, you'll have a similar thing, I think, later on. It generalizes to multiple dimensions, but simple ideas is shown in one dimension pretty easily. You dot it with itself, the only term that doesn't vanish is sigma dwt times sigma dwt. You get sigma squared dt. And then you get a closed form expression, but that's only in limit when your time gaps are extremely small.
We should
Yeah.
say it's related to that kind of convergence of numerical PD solvers where you have to like make space and time small at the same time.
Sure, yeah, Peclet number,
Yeah.
Peclet number. So that's capital T, what's that one? That's
Oh, right, I
constant?
should define that. Yeah, that's the observation period of the process is 0 to capital T.
Zero to go. Okay,
Yeah.
okay, and X in the bracket, so I'm new to this.
Oh, yeah, it's okay. That's
X,
the
yeah.
definition of quadratic variation.
Okay,
So
yeah.
it's just.
It's just a
defined. I
notation.
should have put whole.
And this is the closed form solution for X, right? X within,
It's the close, yeah, I mean, this is the definition of quadratic variation and it has an exact formulation. If you have a kind of SDE with a constant diffusion, then you can write it also as this.
so this is simply X of T, right? X of T
It's
equals.
the quadratic variation of x of t. So this denotes the quadratic variation.
Oh,
It's just
quadratic
weird
Yeah,
notation.
Like, I guess,
That's the stochastic part, it's not the deterministic part, right?
yeah,
It's both. So xt is just your process.
yeah, if this is like XT and you're doing from 0 to T, it's like you're taking each of these differences and then you're just squaring
Yeah.
the differences and shrinking limit. But okay, in practice, we don't actually have the continuous path. In practice, we just have these like discrete observations. So if you want to try to estimate the diffusion parameter sigma, then you just do the natural thing, you discretize it. So this is assuming you have even time spacings. To approximate this DXT, you just do what you observe in your data. And then you would get a corresponding estimate for sigma. So based on how many data points you have, call it capital N, you can just do it as follows. You just sum up all your differences squared, your squared differences, and then divide by the observation period. And that's it. It turns out that this is an unbiased estimator. It's actually even stronger than this. It's a consistent estimator. It converges almost surely even. But okay, I guess yeah, this one's easier to prove. Like this one you can show by kind of just direct analysis. What this says is that the expectation of the estimator will converge to the true value, sigma squared, as long as your number of observations goes to infinite for a fixed time period. So what that corresponds to is just shrinking your granularity to 0. The proof of it, I mean, yeah, maybe I'll show it if there's questions, but the proof of it just, the general idea is you would do the definition of delta xt squared in terms of this, and you would have three terms. And then you would do an analysis by subtracting it off by this. And then you can apply Cauchy-Shorts twice and you show the difference is controlled by delta t to the 1/2. Delta t to the 1/2 basically comes from the middle term when you expand dxt. It's going to come from this term times this term, and you do Cauchy-Shorts. You get delta t to the 1/2. But the main takeaway here is that one, like it's true that our estimates get better as you increase your observations, but they really depend on how fine your time granularity is. So if you have very big jumps in your data, you probably won't have a very good estimate for your diffusion. Another thing to note is that like technically we're estimating sigma squared rather than sigma, but it doesn't really matter at all. You can flip the sign and it'll be exactly the same distribution. You can see this pretty easily because if you look at DWT, these are always normally distributed with mean 0. So if you flip the sign, it's just symmetric. So it's no problem. It's the same thing in multiple dimensions, you just rotate around. And finally, there's a bit of generality here, actually. It's not just for OU processes. This will work for any constant sigma. So as long as the diffusion is constant in this term here, then it'll work as long as your drift is bounded. Then you can.
But DWT, you don't parameterize that. You because derivative of the Brownian nose is very difficult to get, right? So
Yeah, like this is just the differential. I mean, the derivative of Brownian motion, like the white noise, doesn't really exist formally, but that's why I think stochastic differential equations are usually written this way, because this is defined. This is n0 dt. So I think that's why we do it like this. And yeah, if you're simulating data, that's actually how you do
you
it.
can quantify that using data, right? So or you don't optimize this one. You don't.
No, you don't this is just part of your data generating process. So if you're generating data, like simulating data, then we actually update our steps accordingly. Like you take a time step, and then the noise that you add is you sampled from a normal distribution with mean 0 and variance delta t.
If you have real data, so and it has and you know that real data has a Brownian noise, right? Brownian motion.
Okay.
So can you quantify this part using pre-processing?
Yeah, you
Yeah,
can
that's-
quantify sigma. So that's what we're estimating. We're estimating the parameter sigma with
Yeah.
Yeah,
Yes.
And then-
the previous-
And then the two terms together are going to be your stochastic part. Okay, yeah.
This is the estimate for sigma.
Okay, yeah.
No. Okay, yeah, so this is how we would estimate sigma. We still need to estimate, all right. Before we estimate the drift B, this is just a note about how you could estimate sigma in a multivariate case. It's very similar. Basically, if you denote sigma as a matrix, like a square matrix, then you could identify all of its entries. And you would do this in a natural way where, remember, basically, if you had one dimension, it was just the quadratic variation divided by time. Here, we can identify all the diagonals by doing the quadratic variation of the ith process with respect to time. And then the every other non-diagonal entry is just going to be given by the quadratic covariation. So estimating the diffusion is, it's like the formula is relatively simple. Like your degree of accuracy depends largely on your time granularity of your data, but estimating this is not so bad, especially for a constant diffusion. Estimating the drift is a little bit more involved. The way that it's done in this textbook by Pavliotis is by maximum likelihood estimation. So yes, I'm sure like all of you are quite familiar, but okay, we'll just do a quick summary of just the process itself. If we have a bunch of different probability measures, which are each parameterized by some theta, we want to figure out the theta hat that best aligns with our observations xi. So like the classic example is if you have a normal distribution, we just parameterize just by its mean mu and variance sigma squared, then you're trying to basically to determine the optimal theta, you have a likelihood function which is proportional to the density. Each of these are parameterized, and then you would just apply this density on your observations, and this is what you're trying to maximize. So this would be the definition in the simple case where we have a one-dimensional normal with IID observations. If we're trying to generalize this to a stochastic process, it's a little more complicated. We don't have a fixed random variable. We have an infinite collection of random variables. But we could apply similar ideas. Our observations instead are sampled from different time steps, and I'll give an heuristic derivation of the likelihood function for a stochastic process xt from an SDE. Basically, we can do this kind of Markov time step analysis. We can look at each step, xi plus 1 given xi, for every I from start to finish. And what we notice is that this conditional distribution is always normal. This is because of the fact that in the special case of an OU process where we have additive noise, it's always a Gaussian process. So this is exactly normal in this simpler case. But the one difference with the really easy case of just a straight up normal random variable is that we have shifting parameters with our observations, because the mean will be the mean of xi plus 1 given xi is just going to be where you were at the previous step xi plus where you drift deterministically. And then the diffusion, well, in this case, it's constant. It's just sigma squared delta t. So you could discretize this law. You just plug it into the normal. You get this. And some people actually use this directly as the likelihood function. We've seen that the literature is a little bit split. So this can indeed be used as likelihood function. But what Pavliotis textbook does is they actually consider the Radha-Nikodym derivative of this law with respect to Brownian motion, which I think is analogous to in the random variable case. This basically is a Radha-Nikodym derivative with respect to Lebesgue measure, but here, because we have a stochastic process, it's going to be absolutely continuous, not to the Lebesgue measure, but to the law of Brownian motion. And in the same way, you can do this time step analysis to discretize Brownian motion, and then the Radha-Nikodym derivative is, because it's discrete, this heuristic argument is just dividing one by the other. And one thing that you may notice is that our final answer, when you divide these two, it keeps every term from here except the first one. So you still have the last two, but the first one vanishes when you divide. The reason is for the same intuition as before. We have a quadratic variation term. And the only thing that is, well, the thing that's most relevant is going to be this dWt squared part. And that's the part that we're dividing by. So that's the heuristic argument of how you could get this discretization for the likelihood function for a stochastic process. And
Question.
yeah,
We don't think the heuristic argument is very strong though, so.
yeah, I mean, yeah, I don't know if I want to get into that whole can of
So
worms.
you're saying that the most relevant part is this dWi squared, right? Is it because the other part is smaller?
Yeah, because this delta xi squared by definition is going to be like you plug in the definition of your SDE. It's going to be bi delta t plus sigma dWt. Like you have
Yeah.
delta xi is bi delta t plus sigma delta wi.
Mhm.
And then when you square it, we're only keeping sigma squared delta wi squared. That's the argument. And
As we said in the
Yeah.
previous slide, like the delta W times delta T kind of goes to 0 and delta T
Oh.
times delta T goes to 0.
it's not, yeah, it's a weird argument though, because one thing that, because we're trying to actually derive for the multivariable case, and there's something that we don't like, which is that here there's actually a delta T here. So if you were to expand all of this fully, I don't think you would technically get the cancellations, because even though we're like the most vanishing term, delta t dot delta t, it'd be delta t when you divide by itself. So I don't know. But this is how they derived it. I think there's a more rigorous argument with Gersonov's theorem, which tells you that any STE with drift can be reparameterized as a Brownian motion with this change of measure. And this bottom quantity, at least the continuous version, is exactly this Radon-Nikodym derivative for this change of measure. But I didn't fully understand Gersonov's theorem yet. So that's all I have is the heuristic argument, which has, as Joe pointed out, a bit of a weird kind of analysis.
Say again why dt goes to 0 before. You said it in the beginning.
Oh, yeah, I mean, it was like a homework question we had, was like proving quadratic variation of dt is 0. It's, you do a mean squared limit, and I don't know, if you're curious, I could pull up my homework, but right now I can't remember it. But yeah, I do remember this, yeah.
And also, if we, in maximum likelihood estimation,
Yeah.
the ground measure is different, then I think the answer in general is different.
What's the ground measure?
Oh, I mean, the measure with which you're taking the density, like.
Yeah.
Below it's Lebesgue before, but then it's the Brownian.
Yeah.
Measure, so it changes the resultant.
So I
Yeah.
did one experiment and it didn't change very much. But then I tried for multi-dimensions and I couldn't get the optimization to work for the Radon-Nikodym one, but yeah, we don't really
yeah.
know.
I mean, I
So-
suspect it probably doesn't matter that much in this simple case where you have Gaussian processes, but like they're both,
It worked for the simple case, yeah.
Like the top. But not the bottom.
yeah,
Yeah, yeah.
this is the default. This one
Yeah.
probably gets used a bit more actually in the literature, but we also have seen this one pop up quite a lot, including the textbook. But yeah, it's weird. Like I try to look up likelihood functions, like kind of by definition, if there is a measure in which your original density is absolutely continuous to, then you're like the definition of likelihood function is the Radon-Nikodym derivative. And it is true that this density is absolutely continuous with respect to the Brownian motion measure. Like that is Gersonov's theorem. Not that I completely understand that, but yeah, that's the theoretical motivation why people use this, but we haven't noticed much difference in practice between the top one here and the bottom one here in empirical evaluation.
So is there any, don't you think B1 and sigma square might be dependent at the end after you finalize this equation? So don't you think B1 and sigma square might be highly dependent?
Yeah, so we found that like in this simple case, when dt, your time granularity is very small, then it works, it seems to work that you can kind of solve them independently. But when your time granularity is bigger, this like the closed form quadratic variation solution for sigma doesn't really work anymore. So you have to combine them both within the likelihood estimation. And there does seems to be some dependence and probably even stronger dependence when there's multiplicative noise, so heteroscedastic
Don't
noise.
say that, yeah. So because when I'm seeing its application to hydrology, so we had similar thing before, and it's very hard to isolate beta 1 and sigma square, specifically when you are using daily data, right? And that's why people started to use hourly data or didn't use these methods for daily data, because it's very hard to split the information between B1 and sigma square.
Mhm.
Yeah, and in hydrology we have that multiplicative or whatever you call it noise, right? It's not additive, and that makes things a little bit more
No,
complicated.
it does make things even harder. But yeah, I think to reiterate Joe's point, I think you can theoretically separate them because of let's go back a few slides. You can theoretically separate them because of these laws. Like when you look at the quadratic variation, it does separate out. The only thing that matters is the Brownian motion part. So in this sense, you can separate out the sigma. Like that's kind of what this line says. But the caveat is that this only holds for infinitesimally small granularity. So I think in practice, yeah, you observe that it is harder to separate. I have less.
So the
experience.
NURBS paper that we saw, they just used both of them together. They're solving for both of them together. They didn't separate it out, so.
Yeah, like here in Pavliotis, they assume that sigma squared is known using the previous estimate. And then the only parameter they're optimizing over, as we'll see here, is this, what they call alpha, the linear coefficient in the drift.
Yeah, for hydrology work, I think sigma squared is a function of xi, you know,
Mhm.
and
Yeah.
so it's very hard to.
So that would be multiplicative noise.
Yeah,
So
you
we'll
get-
get to that
yeah.
later.
Joe will explain that soon. I'm just going to quickly explain, okay, given this likelihood function that we got, okay, this is assuming we're using the bottom one, not the top one. So I'm jumping a couple steps, going from here to here. I'm both making it continuous. So this is the discrete version, and I'm taking the log. So we can just maximize the log likelihood instead. But you exactly this, like we're just keeping basically this term or these two terms. And then, yeah, you just use calculus, you set the derivative to be 0, and then we get a closed form. This is one of the few SE cases where you have to get a closed form for the MLE. It's given as a ratio of 2 integrals. And yeah, I put the discretization next to it. The main point I want to say about this estimator is that, yeah, it's also asymptotically unbiased and it's also consistent, but it's in a different sense as the estimator for sigma squared. For sigma squared, we saw is as you blow up your observations, but you fix the observation period. So that means you're shrinking your time granularity. In this case, for one, okay, we need stationarity of the process and we need to expand our time horizon. It's in this sense that we have asymptotically unbiased. You need to increase your observation period, and then this will converge to the true one. And
So Pavliotis did just one simple experiment with this 1D case, which you'll see on the left here. I did one example of what the process will look like, the Ornstein-Uhlenbeck process. And you see that as we increase T, but we're keeping delta T constant, we see that the error in the drift estimation goes to 0, but the error in the diffusion stays quite constant. And that kind of follows what Vince just said with the theory, that diffusion error depends on your time granularity and drift error depends on T, big T.
This is based on simulation study, right?
This is simulation, yeah. And then on the right-hand side, we have a slightly different thing. So in Pavliotis, they assume that the drift term is like minus alpha xt dt. And they assume alpha is positive. But if you make alpha negative, we get the xt kind of blowing up either to positive infinity or negative infinity. And we see that our theory also breaks down for this. So the diffusion error kind of starts to blow up as well. In this case, as we increase T. Yeah.
I didn't quite understand why the error in diffusion isn't going to 0.
So as Vince said, the error in diffusion is given by this, right? And this only depends on, well, C depends on other stuff, but it mainly depends on your time granularity. And in the simulation study I'm showing, the time granularity isn't changing. So it just stays constant.
Oh.
Only T, big T is increasing.
Delta T is.
Yeah. Okay, but we also expanded Pavliotis's experiments by holding T constant and increasing N. So that changes your time granularity as well. And we see that the diffusion error decreases as we increase the number of observations, while the drift error stays quite constant because we're not changing big T. And then if we hold N constant, so the number of observations, and delta T is decreased, then diffusion gets better, while drift becomes exponentially worse because big T is decreasing as dt decreases. So these kind of confirm that theoretical intuition, and we also see that there's always this kind of clash between estimating drift and estimating diffusion. There's no plots here where both of them are decreasing at the same time, which is a bit frustrating, but we'll see later there's kind of a solution to that. Another experiment that they did was stationary bistable process. So this is a polynomial. We want to estimate alpha and beta. And we can see that as t increases, the errors of both of those are decreasing as well. Okay, so now we'll return to our presentation from a couple weeks ago where we went over Wang et al., which is the NURBS paper. And they consider two cases for different types of noise. One is additive. So this time it's multidimensional. So we're looking to estimate the matrix A and the matrix G. And in the multiplicative case, we have G as a function of xt. So this can be represented as like a block matrix where G, each component of G is being multiplied by xt, and then it's being multiplied by the Brownian motion. So importantly, they show that the generator for both of these SDs, the multiplicative and additive, is identifiable with probability 1. So basically, if you randomly set A and G, we can find A and G transpose for both equations, given the observational distribution. Okay, so one important point is that, you know, we're kind of always trying to make things Gaussian just to make things nicer. So in the multiplicative noise case, I think Pardis pointed out in her first presentation that heteroscedastic processes, even though they kind of may look Gaussian, are not necessarily Gaussian. So we're still going to approximate the increments of the xt process in the multiplicative noise case with a Gaussian. And yeah, we're basically just doing that with equation 8 here. So we're assuming that these increments are Gaussian given the past. So xi plus 1 given xi is normal with mean set as the kind of drift term. And the covariance matrix is given by sigma squared of dt. Okay, so Vince went over the likelihood for univariate processes, but now we have multivariate processes. It's basically the same. Now we're just using multivariate normal densities. So the transition densities Pxi plus 1 given xi are now multivariate with mean mu I and sigma I. So in the additive noise case, we're plugging in mu I is equal to xi plus a delta t, and sigma I is delta t g transpose. And we have something similar in the multiplicative noise case. Just a bit of a different covariance matrix. So Wang et al. Uses BFGS optimizer to solve this equation 9 to optimize. So they're minimizing the negative log likelihood and solving for the theta parameters that we're interested in, which include A and G transpose. Okay, so as we saw in the univariate case, adding observations through a finer grid can decrease the errors in G transpose, which is the diffusion, but can't really help A, finding the drift parameters. And increasing T while keeping dt constant can decrease errors in A, but can't really, but actually it increases errors in G transpose for some reason. Yeah. We don't know. In fact, we'll see here, down here, these are our processes that we kind of copied from Wang, and they are not stationary. So
So how does that? Like, hit the previous?
I don't know how that kind of connects. I mean, they don't, no one really talks about stationary all that much. I mean, people either assume it or they don't, I think, and
Stationary is used in the proof of asymptotic convergence, but you still have it as an estimator, obviously. I think they're just
Hmm.
using it.
Yeah.
It's my understanding.
Would you not have convergence then? There's no proof convergence on multivariate case?
well, for the sigma squared, it still works as dt goes to 0. But as a log likelihood, I mean,
If
It's
all your
just-
eigenvalues are negative, I think it's stationary. And then they should also theoretically converge. I think these just happen to be not that case.
so here I just did some experiments with testing the sensitivity of the negative log likelihood. So as we add some perturbation away from the true A or true G, we see that A is more sensitive to large perturbations and G is more sensitive, or the likelihood is more sensitive to small perturbations in G than in A, but it's not a big deal. So here we're just recreating the experiments of Wang. So on the left-hand side, we have the additive noise case. And you see a realization of one trajectory of the 2D process here. And then on the bottom here, we have the errors of both A and G going to 0 as we increase the number of trajectories. So before we only had one trajectory in the Pavliotis case, but now we're increasing the number of trajectories and we find that both of these can go to 0. And it's a similar thing with the multivariate multiplicative noise case on the right-hand side.
So you have a two-dimensional system here, right? So
Yeah.
And okay, so it can be like for example, precipitation and ET, right?
Yeah.
Okay.
Oh, it's 2D.
Okay, so one question that we got asked in our last presentation was about random starting points for each trajectory. And we found that even if we use random starting points, the number of trajectories, as they increase, the mean squared error kind of still decreases, which is nice, but it has a different starting point. So here, when we have 5 trajectories, the log 10 MSE is like above -1, but up here it's like -2. So it's better to have the same starting point, but having different starting points seems to be okay. And I also tested the number of dimensions. So as we increase the number of dimensions, the MSE doesn't seem to increase meaningfully, which is promising. And
Either way, I was saying
Yeah.
skip it if you want to. Okay.
And your two-dimension should be independent, right? Or they can have.
no, they can be dependent.
Yeah, I don't know, I don't think this is the most important slide. It's basically just, okay, the state of the art for parameter estimation has just a few drawbacks. One is like pretty much every paper we've seen in terms of evaluation is limited either one-dimensional or two-dimensional. Like we haven't really seen many meaningful parameter estimation experiments on higher dimensions. And they also, there's usually a restriction on what kind of functional model you use. So usually they're simpler too. And finally, everything that we presented in terms of the method, they are all restricted by limitations in discrete observation. So we have theoretical guarantees for basically continuous observation, but that's not usually the case. So there's a lot of research actually about just the debate of what's the error because of discretization and what are the ways to get around it, but that's not the focus of this.
It also seems like everything you presented was linear. The drift was linear.
There was one case that was very quick. It was this, they call it a bistable process, this one.
Oh,
But you can do that because this has constant drift, you could still estimate that one. And then this one, it's still the same process of like just different things get plugged into the MLE, and it's a slightly more complicated linear system, but yeah, it's kind of what we looked at already for monomials, I
We
think.
kind of need the linearity, right, well,
Yeah, I mean, that debate, I don't know.
Oh,
There's a lot of I don't know, like a lot of these existence uniqueness proofs, they assume linear growth, otherwise your solution blows up, but then people still do this stuff in practice, so it's, I don't know, fun and confusing. Like,
So can you use, for example, gamma or exponential instead of, because your polynomial is still linear, can be considered somehow linear, right? But for example, gamma or exponential can be drift there.
as the drift, I think that would blow up very fast.
that'd be like a Levy process.
Really?
Oh, wait,
As the
I
drift
see.
term.
All right, he's talking about what we will talk about later with the
Okay,
memory stuff.
I'll trust you for that. I'm not sure. I think he'll probably answer better. Okay. There's a few other things that we realized in the past couple of days, actually. So, okay, first point is that a lot of us have been interested in a non-Markovian parameter estimation. If our process depends not just on the current time, but the update step depends on the entire path. So if basically if the SDE has memory, and yeah, this should have, yeah, like a lot of things, I think in hydrology especially, are modeled like this. And I think, yeah, equation 11 is
Well, in fact, the Manton paper, which comes up with equation 10, they're directly comparing to a method that uses functional historical linear models, and that's equation 11, which I've done work in for. Yeah.
Going on about this Manton paper. So this is a paper from 2024. It's very recent. It's called like signature kernel something.
And also one of the authors there is
Mogensen.
Mogensen, which will be at our SIAM event this summer.
Yeah, and there's something that we realized yesterday or 2 days ago. This is, I think, quite interesting. If you have an STE that looks apparently Markovian, because this is just a multidimensional Ornstein-Uhlenbeck process, it can actually not be Markovian if you have 3 dimensions or more, which I think is one reason why the Wang paper restricts to 2. But okay, here's why. If you have your drift matrix be in such a way that xt2 depends on xt3, but xt3 depends on xt1, because of the nature of the differential equations, you'll see that finally dxt will actually depend on the entire path of xt1. So I'll go through step by step. So reading off this equation for the second component, dxt2 depends on xt3 dt plus, okay, some noise. But then if you look at xt3, reading off this equation, it depends on, in the same way, xt1 dt, and okay, there's also no noise here. So if you assume that xt3 starts at 0, then you could write xt3 as an integral of the first one. And then you can substitute this in to our original one. And this tells you that the second component depends on the first, but not in a linear way. It depends on it in terms of this integral. So that's something that, I don't know, I didn't foresee happening. I kind of took for granted just because of notation that like this would mean in any dimension that your process will evolve in a Markovian way, that it will only depend on previous steps. But if you were to unfurl it to its basic principles, you could chain things and actually get more sophisticated relationships.
And this example comes directly from the Mogensen paper.
So, but if you have 2 variables and they depend on each other,
That's okay. 2 variables is fine because you can't do this, like this step here kind of terminates and you can't plug back in. You need at least 3. You need like parent of a parent to get an integral in your drift.
theorem in the first where she said that STEs are Markov processes, so is there like a assumption there, which this is not
That's a
something?
good question. I wonder if that was for one dimensional. I wonder, I don't know, because this does seem to contradict it.
So what did they say about?
Well, I guess we only found this out a couple days ago. We haven't, class is done, so I haven't had a chance to talk to her, but it's a good point that Sharbaj mentioned that STEs by definition are Markov processes, at least in this current form, like if they only update based on XT, but that might have, everything we've done in class, except I think explicit examples are usually one dimensional. So that would be my guess, was that this result holds for 1D and this does in fact break it.
I mean, the Markov means given xt doesn't depend on the previous. So somehow given x to x1, x2, x3, times t. I mean,
I mean, it's a different variable, importantly, in equation 15. So in terms of Markovian and in relation to itself, I guess xt2 would be Markovian.
if you're given xt1 and xt2 and xt3. But if you just restrict now to x1 and x2,
Mhm.
maybe it's not.
Yeah.
You have a latent.
This paper was just doing independence testing for these type of memory SDs.
Yeah, I think this was their only case of a memory SD also. And we were confused initially, like, how is this a memory SD? But there's a lot of papers, a lot of authors on this paper.
Who's the-
Manton. I think Derek mentioned this paper a few months ago.
It's brand new.
Yeah.
The topic is called memory SD.
There's a bunch of different names for it. It's like path dependent SDs. There's
Yeah.
differential delay SDs.
Distributed delay.
Yeah,
Yeah.
distributed delay SDs and I guess memory SDs.
I think we call it
Yeah,
memory.
I think we say. You know,
Yeah.
So they do independence testing. How do you do that?
huh?
Some signature kernel.
Signature
Uh,
kernel.
yeah, I didn't understand the paper. Yeah, they didn't do parameter estimation. They just did independence testing. I assume they got the correct, structures. And then I was curious because we actually were able to get the code from Wang's paper. So the what's it called? Generator identification paper. And because I can play around with dimensions, I could actually input this example because this is actually equation 12 coincides with the additive noise model just with 3 dimensions. So I just inputted this and I was curious how well parameter estimation would do. And basically what I found was if I do this exact example with the scaling of 0.3 done in Manton, and I used as default, I gave 1,000 time points, it did very badly for estimating the drift. I had mean square error over 40, but then just by switching the scale of the Brownian motion, I just divided it by 10 and using the exact same like parameters otherwise, it then succeeded. Like it got a pretty good estimate. And what I just ran actually, I reran with 0.3. So I reran this one, the exact case in Manton, and I just increased the number of points in the process. Like I made it instead of 1,000, I made it 10,000, and that actually worked. It got really good, like error. So yeah, you basically you can estimate these parameters, but it might come at the cost of a lot of data.
They use the likelihood method.
They use a likelihood method to estimate both sigma and mu, and yeah, there's probably ways you can make the method also more effective. There's a lot of papers, mostly in the 90s, that talk about just how you can fine tune likelihood functions and maybe add points. Like you can, I think that's what the Peterson paper said. You could, if you have like a granularity, you can get subgranularities by basically adding more data according to other estimates. So there's a lot of things, but it does look relatively, I guess, promising that you could embed kind of these memory SDs as a linear in higher dimension and then do parameter estimation. And then the last thing that I think we want to bring up is that, okay, you can generalize further and then we can recover another form of SDE. So we previously had just constants here for the Nanton example. But if you make them time inhomogeneous and you just do the exact same computations, then you could get something that looks fairly general. We're wondering, I don't know, I'm very bad at convolution, but we're wondering if we could rewrite this without loss of generality. I think Joe's fairly convinced that you can. Like this can just be viewed as a convolution, which is used a lot, kind of as definition as a ST with distributed delay. So we're wondering if distributed delay STs can be embedded in 3-dimensional or higher dimensional linear STs. Just does kind of seem like you can. So that's yeah. Anything else, Stab?
Yeah, it's good.
Question in linear?
Oh, I mean, we're just
I know it's
using,
linear. If you have a distributed delay. Oh, you mean the
just
one with
linear,
the
it's kind of easy to solve.
autocorrelation, like the one with the convolution?
yeah. Like here we have the same time parameter inside. Like usually there's an offset for
Yeah,
convolution, so.
maybe you can guess the A and then see the difference.
Yeah, pretty much. It's just like, can you reduce parameter estimation in SD like this to just guessing A? Yeah, I guess this would be A of T, but yeah.
But then if you can do this in continuous variables, maybe you can also do discrete ones.
Yeah, maybe. There's a paper that looked at, it's a paper you sent me. They looked at parameter estimation of time varying diffusion, like this parameter here dependent on time, and they used a neural network to try to solve a likelihood function, and it worked really well. They were able to recover all the time trends of the diffusion. They only had one value on drift though, because it's probably harder.
Yeah, R is gonna present that paper in a few weeks.
Oh, nice.
Is there any chart there?
Shocking.
Yeah. Okay. So I think probably you guys, what I'm going to show is something that you guys already explained that, but in hydrology, we are looking for this. So dq over dt. So we can assume it's x, right? So as alpha q